Okay, in this chapter we're going to learn how we can use derivatives to apply it to functions and analyze functions using derivatives. The first thing we want to talk about here is extrema. And so let's talk about extrema on an interval. And basically we can use calculus to determine the optimum points on a graph. We may be looking for a maximum value or a minimum value in a particular neighborhood. In that case, we would be looking for relative extrema rather than absolute extrema. If we're looking for the maximum or minimum of the entire graph or the entire domain, then we would be looking for absolute extrema. Now some texts call relative extrema local extrema, and absolute extrema, they might call them global extrema. But in here I'll use the terms relative and absolute. So the definition of extrema basically says this: if a function is defined on an interval that contains c, then f of c is the minimum of if f of c is less than or equal to all values of f of x for all x on the interval. So if we have a certain interval, f of c is the minimum basically if f of c is the smallest y value on that interval. And then of course f of c is the maximum of f on the interval if f of c is greater than or equal to all of f of x on that interval. So in other words, if f of c is the largest y value on that interval, then f of c is a maximum. So the minimum and maximum function on an interval are called the extreme values or extrema. For a singular, you can say extremum of the function on the interval. These minimum and maximum values on an interval are called the absolute minimum and absolute maximum. Okay, so let's take a look at some examples here, and let's see if we can shed some light on this. So if you look at this graph here, you can see that over this interval, you know, because I'm only showing you the graph from here to here on the x-axis. So if you look at the graph only from only across this interval, well, you can see that the absolute minimum for this function is actually y equal -7, or f of 5. So f of 5 is -7, and that's the lowest, that's the smallest possible y value over this interval. And there's actually the absolute maximum on this interval. Well, there's actually two places where it occurs. There's only one maximum, but there's two places where it occurs. Right here at this point, you have the point 2, 0, and then over here you have the point 8, 0. So basically 0 is the maximum value over this interval. Okay, now for this function, the absolute maximum occurs at the very right of the domain. So the maximum actually occurs over here, and so it looks like it's around 20. So the maximum is 20, and then the absolute minimum is actually down here. The lowest value for the graph over the interval is actually down here. It's -32. And we'll talk about this value here a little bit later. This is actually what we call a relative extrema. But for now, I'm just talking about the absolute extreme value. So this is the lowest value on the graph, so -32 is the absolute minimum. And this is the highest value on the graph, and that point there is actually the point 720. So therefore, 20 is the maximum of the graph over the interval that I'm showing here. So just over that interval that I'm showing. Okay. Now, the extreme value theorem basically says if we have a continuous function on a closed interval, like we do down here, so So like if we have a continuous function on the closed interval, let's say we go from 0, let's say we just go from 0 to 7. Let's see, where would 7 be? 7 would be right here. So let's just say we have this closed interval from 0 to 7. Alright? Basically what it's saying here, that as long as this function is continuous, and this function down here is continuous, then f will have both a maximum and a minimum on the interval. In other words, we're guaranteed that we'll have both extreme values on the interval. And you can see here that if you look from just from here, x equals 0 to x equals 7 for the interval, you can see that I have a minimum of -32 here, and I have a maximum of 49 here. Okay, now again, only on the interval from 0 to 7. So we get a minimum value and we get a maximum value. Now here I want to look at this function, and I'm only going to consider the interval from -3, so -3 would be right there. So from -3 out to +7. Okay, so there's 7 right there. Okay, so we only want to look at the portion of the graph that runs from where x is -3, so that would be here up through here, and then of course it would stop right here. Okay, well here you can see that over that interval from -3 to 7, the minimum value is actually way down here at -81, and the maximum value is actually way up here at 49. So it turns out that when you're looking for absolute extrema, if you're looking for absolute extrema on a closed interval, sometimes the extrema can occur at the endpoints of the interval. Like here, the extrema occurred at the endpoint 749, and same thing here. But sometimes the extrema could occur at a value within the interval. So we need to figure out, how can we determine what those extrema are on a closed interval, and we'll get to that. Okay, so let's talk about, now I want to talk about relative extrema. So for relative extrema, basically it says if there is an open interval containing C on which f of C is a maximum, then f of C is called a relative minimum. Okay, so if you look at this graph down here, you can see that obviously this point right here is not the maximum of the entire graph, because obviously these points over here are higher, but there is an interval, say this interval here, that would maybe define just this portion of the graph, and certainly on this portion of the graph that point is the highest value. So in that case we could say that this point -2, 0 is a relative maximum. So basically we get a relative maximum of 0 at -2. And then down here, if you look at just a small interval around this point, then even though this is not the lowest point on the graph because there's values over here that are lower, but this is the lowest point in its neighborhood. So basically if this point is the highest point in its neighborhood, it's called a relative maximum, and this point is the lowest point in its neighborhood, it's called a relative minimum. Now if you want to use layman terms for this, this is like a peak and a valley. So at a peak you get a relative maximum, and at a valley you get a relative minimum. Now there's a couple of ways you can do that. If you notice with this one, with this graph, there's this smooth transition where the graph goes from increasing to decreasing, and then down here there's a smooth transition where it goes from decreasing to increasing. And so you'll notice we get relative extrema at those values. But over here with this one, it does go from decreasing to increasing here at this point, but it's not a smooth transition. It's like a jerk. It's like a sharp corner transition. So, but still that is a relative minimum. So we do get a relative minimum of 3 at -3, and we also get the same relative minimum of 3 at +6. And then here, right here, you get a relative maximum of 10.429 at 1.5. So basically, this definition might be a little hard to follow, but hopefully the pictures here explain to you that this is a relative maximum, this is a relative minimum, and over here these two lower points are relative minimum, and then this is a relative maximum. Okay, so one of the things that we need to be able to do to identify relative extrema is find critical numbers. Now, a critical number, first of all, for C to be a critical number, the function has to be defined at C. Okay, so if f is defined at C, C is a critical number two ways. One, if the derivative is 0 at C, then C is a critical number. And two, if the derivative is undefined at C, C is a critical number. Okay, so let's identify the critical numbers. So here's a function. So what I want to do is see if there's any numbers that make the derivative of this function 0 or make it undefined. Well, the derivative of this function is 9x squared minus 36x. So that's a polynomial, and it's defined for all real numbers. So I'm not going to get any values where it's undefined, but I can figure out what makes this derivative 0. So all I have to do is set it equal to 0, factor it, and then solve this equation. So you can see, and when it's in factored form, you can see that if x is 0 or if x is 4, then the derivative would be 0 if x is 0 or 4. So those would be the critical numbers of that function. And basically what we found out is, since those values make the derivative 0, then at those values is where you're going to get horizontal tangent lines. Now this function, you would have to use the quotient rule, and I'll let you show that this is the derivative that you'd get. Now this derivative would be 0 if x is 1 or negative 1. So 1 and negative 1 are actually critical numbers of this function. Now for this function, you're going to have to use the product rule. So you can use the product rule to find the derivative, and this is the derivative for this function. Now this function, if you set it equal to 0, then you would have to solve the equation 3x plus 2 equals 0, and you could get x equal negative 2/3 as a critical number. And then if you want to know where this function is undefined, set the bottom equal to 0. And in other words, see what makes the denominator 0. And of course, you can probably easily see that if x is negative 1, the denominator is 0, so that would make it undefined. So negative 2/3 makes the derivative 0, and negative 1 makes the derivative undefined. So those are both actually critical numbers. Here's another one. If you take this one, and then you can actually show that the derivative is this. Okay. All right. Well, you'll see that the critical numbers are 0 and negative 2. But one thing you need to be aware of is that x equal negative 1 is not a critical number, even though it makes the derivative undefined. And the reason is because, remember, I said to be a critical number, the function has to be defined there. So if you go back and look at the function, you'll see the function is not defined at negative 1. So therefore, negative 1 is not a critical number. So for this one, the only critical numbers are 0 and negative 2. Now, you do get a vertical asymptote at x equal negative 1, so it is an important value, but it's just not a critical number. All right? Now, on the next video, we'll talk about how we can use these critical numbers to find extrema.